In this video, we will talk about the SI unit for time, that is second. So what is second? Well, according to the latest definition, the second is defined as the duration of 9,191,631,770 periods of the radiation corresponding to the transition between the two hyperfine levels of the ground state of the cesium-133 atom. So it seems like a very long and very complex definition, but I will explain it to you in detail. So hopefully you're gonna understand this definition a bit more thoroughly. So it's simply saying that a second is the time that the cesium-133 atom takes to vibrate. About how many times? About this many times. Let's say about roughly 9 billion times. About 9 billion times. So 1 second equal to the vibration 9 billion vibrations of cesium-133 atom. So first of all, we're gonna go through the history, then the mechanical clocks, then the era of mechanical clocks, then quartz crystals, and then we're gonna go through the atomic clocks from which this definition was finalized. Let's first go through the history. So in the ancient history, we have the ancient Sumerians and the Babylons. So in the previous video, I talked about the meter. In the meter, if you haven't watched that video, I highly recommend to check that out. Also, after watching this video, so in the meter, we know about 1 meter, 10 meter, 20 meter. So basically, I'm trying to say a meter is based on decimals. We have 10, 20, 30, 40, 60, 70, 80, 90. 100. So this is the decimal system. Meter is based on decimal system, but when it comes to time, we see that in 1 minute we have 60 seconds, in 1 hour we have 60 minutes. So why didn't we choose 100 as a base? Why we chose 60 as a base? So the obvious, the most straightforward, the simplest answer is due to conventional reasons, because that was done from the very start. The ancient Sumerians and Babylons used the sexagesimal systems. So they used sexagesimal system, which had the base of 60. And that is why when we talk about 60, when we talk about the degrees, about 360 degrees. So why 360 degrees? It is also because of the sexagesimal system that the ancient people were using at that time. So that also was applied to the modern times. So we didn't change it. It is still based on the sexagesimal system. So at that time, in ancient times, a second was not the sexagesimal subdivision of the hour. It was the sexagesimal subdivision of the day. So in the ancient time, let me write it. So you're gonna get clear about it. A second was, in the ancient times, was day divided by 60 multiplied by 60. So that was the definition for a second. But according to the modern times, it's based on hour. hour divided by 60 multiplied by 60. So at that time it was the sexagesimal subdivision of the day, but in modern times right now it's the sexagesimal subdivision of the hour. So another important fact was that before the 14th century, before the invention, before the time the mechanical clocks were not invented, an hour was just an hour. It didn't have any 60 divisions, meaning it didn't have 60 seconds, because the clocks at that time were just not accurate enough. So in ancient, when we talk about the ancient civilization, we know about sundials, water clocks, etc. So these were used, but before the 14th century, the the clocks were just not accurate enough, just to measure minutes. It was just based on hour. So now we're gonna talk about the mechanical clocks, the era of mechanical clocks. I think I'm gonna write it with red, main heading, mechanical clocks. So at the end of 16th century, the mechanical clocks began to introduce, with the invention of mechanical clocks, they began to introduce I'm sorry, seconds, not seconds, minutes. They began to introduce minutes into the clock itself, where because of the increasing accuracy of the mechanical clocks. So but still the the problem for second was just far from over. So when was what was when did we created a mechanical clock that was accurately able to define or measure a second? So that was in 1656. Let me write it down. In 1656, by the Dutch scientist Christian Huygens. Christian Huygens. So this scientist introduced the mechanical clock that was able to measure a second. It had a pendulum that was roughly about the length of a meter, roughly under 1 meter, not equal to meter, approximately equal to the meter. So it was able to measure the second accurately. So depending on the accuracy of the clocks, the second was defined as, let me write it down, the second was defined as 1 by 86,400 of a mean solar day. So I know you're gonna be wondering about this word solar day. What is solar day? Well, a solar day means the rotation of the earth around the axis so that the sun appears at the same spot or position in the sky. So it's just solar day meaning the position of the sun, that for example you have for example, let's say if the sun is at 45 degrees or some spot in the sky, so in the next day it should be on the exact same spot. So that is the solar day. So next we're gonna talk about the quartz crystal oscillator. Quartz crystal oscillator. So with the invention of quartz crystal oscillator, just the accuracy became a far more higher than that of the mechanical clocks, and they were very suitable for timekeeper because they were so accurate. They were more accurate than any mechanical clock at that time. So and quartz crystal, due to the quartz crystal, we were able to redefine the definition of a second, and it also showed that the orbit of the earth around the sun was more stable than that of the rotation of the earth around its axis. So let me write it down, so you're gonna get a clear idea. So it showed precise wait, oh, accurate than mechanical clocks, and also showed that the orbit of earth around the sun is more stable than the earth's rotation about its axis. So when it showed that the orbit of the sun, our orbit of the earth around the sun, is more stable than the earth's rotation about its axis, so it became clear that the first definition, the solar day, the 1 by 86,400 of a mean solar day, was just inaccurate. So in 1956, the second was redefined. In 1956, write it down. 1956. In 1956, the second was redefined as, let me write it down, the fraction of 1 by, it's gonna be a huge number, so I'm just gonna say the numbers: 3155692599747 of the tropical year, for 1900 January 0 at 12 hours ephemeris time. So the definition of second was redefined as the fraction of 1 by 3155692599747 of the tropical year for 1900 January 0 at 12 hours ephemeris time. So what is ephemeris time? Ephemeris time is the time calculated with by the Earth's orbit around the sun, not according to the Earth's axis, because as we talked right recently, that the Earth's axis is not stable as compared to the Earth's orbit around the sun. So ephemeris time was time calculated according to the Earth's orbit around the sun. So this definition was adopted wasn't adopted in the International System of Units. It was adopted in 1960. In 1960, this was adopted in SI. It was not at that time in 1956. It just didn't instantly became of a definition for the SI. It became a definition. It was adopted as the definition for the second in SI in 1960. So quartz crystal, even though we had more accurate timekeeping methods of timekeeping, the quartz crystal was not accurate, also not accurate enough for more precise, more and more precise timekeeping. So we needed more accurate, more. We wanted to have more accurate the device for calculating, for measuring time. So as we know previously about the video on meter. So what was the last definition, the final redefined definition of meter? It was based on constant. It was based on the natural constant. So you're gonna find out that all the SI units, base units of the SI, are based on the natural constants of the universe, based on gravitational constants, based on this constant speed of light, based on Planck's constant. Why these constants are used? Because these are the natural constants. They cannot be changed no matter what. So these constants are the fundamentals for explaining all the definitions of the base units. So when it came to time, we wanted to have a natural number. So we shifted from the quartz crystal to the atoms. So in atom we chose Cesium-133 atom. Why? I'm gonna explain it to you. Let me just write it down. Atomic clocks. Atomic clocks. We have Cesium-133. Why Cesium-133? First of all, why chose atoms? Why? Because of its frequency. We know about that the electron that about the energy levels of an atom, about the energy state. It goes from the higher to lower. It goes to higher when it has higher energy, when it has absorbed energy, but it goes to a lower orbit when it releases the energy. So it was based on this, it was based on that. But why chose the Cesium-133? Let me just grab this photo image. I'm gonna make it large. We have here cesium. Cesium has 55 atoms. The 54 atoms are in stable electronic configuration. They are in stable orbits, but the one atom that is in the most outermost orbit is only one, and that is this one. Because of that one atom, we chose it as the means to calculate the time, because of the stability of the Cesium-133 atom. So first of all, I think I'm gonna show it the definition, and according to the definition I will explain it to you how this definition is explaining the methods of the definition of second, how it is what is saying about it, the definition. So it is saying the duration of 9,191,631,770 periods of the radiation corresponding to the transition between the two hyperfine levels of the ground state of the Cesium-133 atom. So it's saying the roughly 9 billion periods of the radiation. We know, talked about recently, that atom jumps from and lower to higher, but it depends on the energy it absorbed or released. If it goes higher, it means the energy he absorbed. or when it goes to low orbit, meaning he has released some energy. So when it came to cesium, we know outermost we have only one electron in the outermost orbit. So when we're gonna throw in the photons on it, it's gonna absorb energy and it's gonna vibrate. It's gonna oscillate. It will have approximately 9 billion periods, and that will be equal to 1 second. So let me just explain. It says about I talked about the oscillating, going to the higher lower orbit, but it says corresponding to the transition between the two hyperfine levels of the ground state. First of all, let me talk about the ground state. The ground state simply means the lower possible energy state of the electron. Here he tells us about the two hyperfine levels. So what are hyperfine levels? This is the main deal about it. So first of all, let me tell you about the hyperfine structure. Hyperfine structure. So what is hyperfine structure? Hyperfine structure is just the small shifts of the energy levels. Let me write it down. Shifts of energy levels. Why the shifts of energy levels? Due to the interaction between nucleus and electron clouds. So hyperfine structure is basically saying that it is only the hyperfine structure is the shifts of energy levels due to the interaction between between the nucleus and electron clouds. So these number of shifts of energy levels are the hyperfine levels. So here it's saying two hyperfine levels, which means there are two shifts of energy levels. There are two shifts of energy levels. So I think I'm just gonna zoom it a little bit to get a more clear idea. So here now when we are talking about shifts of energy level, there are really tiny small energy levels. So it's talking about the ground state, which means it's in lowest possible energy state, in meaning its natural state. So here the outermost electron, the 55th atom, has two hyperfine levels, two barely visible well, you can't see atom with a visible eye. So there are barely some there are two shifts of energy. So it says about the energy of the ground state of the cesium-133 atom. So here there are two small shifts of energy levels, which are two hyperfine levels. Why there are two? Why the hyperfine level is created? Because this is unpaired. This is unpaired electron. Unpaired electron. So if you wanted have an paired electron, then in the outermost shell it must have two electrons, but instead we have one. So that is why the hyperfine structure is in action, because of this single unpaired electron. So when we bombard the photons, it changes it's oscillate between the two hyperfine levels. The hyperfine and the hyperfine levels, the small energy levels, it oscillate between these two levels at its ground state, and as a result we get a radiation. We get 9 billion 191,631,770 periods of radiation by in this layer of in this boundary of the two hyperfine levels. So that is what it's saying. It's saying just approximately 9 billion periods of radiation in these two hyperfine levels of the ground state of this outermost, the 55th electron of the cesium-133 atom. And I think I found my mistake here. I wrote it down atoms. Wow, good job me. Electrons. Really sorry about that. It was really a interesting yet very difficult topic to explain. So I really hope you have found this video interesting, and I really hope you have understood this definition. And also I also forgot to tell you that these atomic clocks are so precise that they can be off by 1 second every 10 to 100 million years. So you're gonna be off by 1 second only after 10 to 100 million years. So these are very precise. Now you're gonna talk about atomic clocks. Why this kind of accuracy? Why do we need this accuracy? First of all, we know we launched rockets. We have high speed we have satellites that orbit around the sun in many insane speeds. So when you are using GPS, you need very accurate numbers. You need very accurate coordinates in order to in order for your mobile to locate, to accurately pinpoint your location. So without these atomic clocks, you will never had this kind of precise tracking. So I really hope you have enjoyed this video and found this video informative. I'm sorry for taking a lot of time. It's about half an hour explaining this topic. So I hope you have enjoyed this video, and I'll see you in the next video.